Next up is the naming of these aromatic compounds through the proper method, which is the IUPAC names. As you saw in other chemical molecules as well, this is the standard naming system basically. So most of the simple aromatic compounds are named as derivatives of benzene. Benzene is the most common aromatic compound. That is why you can say a typical or a standard aromatic molecule. So for the monosubstituted benzenes, basically, in other words, which have one group or one substitute attached to the benzene, we first write the name of the group and then add benzene at the end of it, and it simply names it. Like NO2, which is the nitro group, so this one becomes nitrobenzene. The rest of the structure is the benzene molecule. C2H3, which is the ethyl group, so it becomes ethyl benzene, and bromoenzene if the attached group is the bromine atom. And then there is this historical nomenclature. So some members of the benzene family have unique names. So they've got a totally different names, you can say, and that were acquired before the IUPAC system was applied. So these are historical names, old names, you can say, before the IUPAC system, and they were adopted and are still frequently used even after the IUPAC system. So with this CH3 or the methyl group attached to the benzene, the molecule is known as toluene. For the hydroxyl group, it is phenol. Then we have aniline with the NH2 group, and the COOH or the carboxylic group is known as benzoic acid. So these are a few examples of these old or historical names which are still commonly used these days. Then we have the di-substituted benzenes. Di stands for two, so these benzene molecules have got two substitutes or two groups attached with them, and the naming of the groups will mostly be in the alphabetical order, and the first named group will always be at position number 1 or attached with carbon number 1. And if a special group is present, then it must be number 1 on the ring. And now there is an older system for this for these di-substituted benzenes, which uses these ortho, meta, and para, or in simple words, you can simply remember O, M, and P. If the location of the substituted groups on the benzene is 1 and 2, we will call such molecule as ortho or para. If the groups are attached at carbon 1 and 3, we call it M, and if they are attached on carbon 1 and 4, we call it P or para. And in the next slide, we will see their examples. So the rules of naming that we saw in the previous couple of slides are applied here for the di-substituted benzenes. So as we saw that these substituted groups have to be alphabetically ordered, so that is why B comes before E. So this one becomes the carbon number 1, and it is 1 bromo 2 ethyl benzene. So carbon number 1 has the bromine and carbon number 2 has the ethyl group, and they are alphabetically ordered. Now because these substitutes or groups are attached at carbon 1 and 2, that's why we can simply call it O-bromo-ethyl benzene in the historical or the old system. Same is the case in the second molecule. Again, this one has got a methyl group and a nitro group basically, and the old name for this whole molecule was toluene, which had one methyl group attached with the benzene ring. So we use that common name toluene plus the carbon number 3 has got a nitro group attached, so we call it a 3-nitrotoluene. And another name for this one can be M-nitrotoluene, because the two groups attached are at the carbon number 1 and carbon number 3 in this case. So this methyl group is at carbon number 1 and the nitro group is at 3. So if two groups are at 1 and 3, we call it M. if two groups are at carbon number 1 and 2, like in this first case we call it O, and if two groups are at carbon number 1 and 4, we can call it P. So this one is a dichlorobenzene, so it can be called as P dichlorobenzene. Now sometimes in the hydrocarbons we see that the benzene molecule acts as a substituent, or it is a group present in the hydrocarbon. So when benzene is a substituent, its name changes and it is called a phenyl group. Do remember that this is a phenyl group, not a phenol group, which is a totally different functional group from this one. So when benzene is a substituent, it will be called a phenyl group, and its formula will be C6H5. There it will lose a hydrogen from it. So we can see a butane hydrocarbon or an alkane with 4 carbons. So it's a butane, and carbon number 2 has this benzene ring attached with it. So here benzene is a branch or a substitute. So this will be called 2-phenyl butane. And similarly 3-phenyl 1-butene. So this one has a double bond in the chain, so it's a butene molecule, and carbon number 3 has got a phenyl group. So 3-phenyl 1-butene is the name of the second example. Next up are a few examples as a homework that you have to draw the structures of the following compounds. So the first one is a benzene molecule. So it's a 6-carbon ring basically. Of the carbons, we know the typical benzene structure. It has got alternative double bonds, so we draw the double bonds, and it has got 3 substitutes present. All 3 are the chlorine molecules. So we can start numbering from anywhere basically. We simply have to make sure that we skip one carbon. So if this is carbon number 1, the next chlorine is attached at carbon number 3, and the last one is attached at carbon number 5. So this will be the 1,3,5 trichlorobenzene. Rest of the structures you have to draw these structures and submit on my email address as usual. This is the homework. Next up are a few reactions of the benzene. So first thing to remember is benzene does not readily undergo addition reactions. So so the addition reactions does not occur very commonly with the benzene. But it typically undergoes a specific type of substitution reaction known as electrophilic aromatic substitution, and the typical definition of the substitution applies here. An atom or a group of atom will substitute a hydrogen on the ring. So one hydrogen atom of the benzene molecule will be replaced by one atom or a group of atoms. And all the benzene reactions, do remember, require always a catalyst. So a special molecule or a special atom has to be there to catalyze these reactions. And the typical of the reactions are halogenation, in which a halogen atom will replace hydrogen, nitration, and sulfonation. So a halogen, nitrogen, or a sulfur molecule typically replaces this hydrogen in the benzene molecule. Okay guys, this slide is about the electrophilic aromatic substitutions. So these are different types of reactions, mainly substitution reactions, which these aromatic compounds undergo. And so here we have an aromatic compound and it is reacting with this molecule represented by EY. So the thing to notice that this molecule has got a electropositive part and a electronegative part. And electrophile means the molecule that or the part of the molecule that likes the electrons. So a phile is for liking and electro is for electrons. So electrophilic means electron liking molecule. So in these substitution reactions, as a general rule, what will happen is that this electro positive part of the molecule will go and substitute a hydrogen atom on the aromatic molecule, whereas this hydrogen will be replaced and it will be attached with the electronegative part of that compound or that molecule. So we will get the products as this electropositive part, or the positive one has attached with the aromatic compound, and we get the HY molecule. So this is the general description. The actual reactions can be halogenation. Same thing will happen. We have a HX molecule. X is representing the halogen atom. So it can be chlorine, bromine, which are the usual ones. And this X will be attached with the aromatic compound, and we get a water molecule as the other product. In this column or in this side, we have written the electrophiles, basically the molecules that likes the electrons. So for halogenation reactions, it will be the X positive. For nitration, it is going to be the NO2 positive that will attach with the aromatic compounds. For sulfonation, it is the SO3 positive group. Then we have the Friedel-Crafts alkylation, in which R positive is the electrophile, and another type of electrophile is RC double bonded with the oxygen, again in Friedel-Crafts reaction, but this is acylation. So we have a look at these substitution reactions one by one. First up is the benzene halogenation. So the halogenation places usually a bromine or a chlorine on the ring. These are the two most commonly used halogen molecules that are attached with the benzene molecule. So the reagent is in diatomic form, Br2 or the Cl2 for bromine and chlorine. And an important thing to remember is we need a catalyst for this reaction. Iron or iron halide are used as catalyst. This iron bromide or FeBr3 is the example in this reaction as the catalyst. So we have the benzene, we have the diatomic bromine or the bromine molecule. One bromine goes and attaches with the aromatic ring, and H, which was attached here, that will come and attach with the other bromine to make HBr. So bromobenzene will be the primary result, and we also get a molecule of HBr in this reaction. So a similar reaction, benzene nitration, this time benzene reacting with the nitro group. So this nitration reaction places the nitro group on the benzene, which is the NO2 group. So the reactant used in this case is nitric acid. The NO2 from this molecule will go and attach with the benzene. A hydrogen, like the previous reaction, will come over here and attach with what is remaining, and the remaining part will be OH negative here. The H joins with it to make the water molecule, and we get the nitrobenzene in this case. Do remember the catalyst for this one as well. Sulfuric acid or H2SO4 is the catalyst, and a concentrated form means a strong sulfuric acid. And we need high temperatures as well. 50 to 55 degrees Celsius are usually recommended for benzene nitration. Again, a similar substitution reaction. In this case, it is sulfonation with the benzene, which places a SO3H group on the ring. Just like the previous reaction, concentrated sulfuric acid is the catalyst, and this is also an example of substitution reaction. So sulfur trioxide is used as the reactant with the benzene, and the molecule that attaches with the benzene is SO3H group, as we can see here, and this will make a benzosulfonic acid. Plus the other product is water, just like the previous reaction as well. Next up are the Friedel-Crafts reactions, and we have got two types, alkylation on this slide, and then there is acylation as well. So in this one, simply an alkyl group is going to be attached with the benzene molecule, and here we have the reactant CH3CCl, which will donate the alkyl group, and here is the alkyl group attached with it, and this is the electrophile as well in this case. So the electrophile actually is this molecule, CCH3 3 times C, which is known as the butyl cation, as it has got a positive charge on it, so it's a cation, plus a 3 methyl group CCH3 attached with the central carbon. So this is the electrophile that attaches with the benzene. So these two molecules are the same. After attachment, it loses the positive charge on it, and the other product will be the hydrochloric acid, or HCl. For these reactions, we need a Lewis acid as a catalyst. In this case, aluminium chloride has been used. So one of the Lewis acid has to be the catalyst in these reactions. So this one is a similar Friedel-Crafts reaction, but it is acylation this time instead of alkylation on the previous slide. And the main difference is in this reaction we place a acyl group on the ring. In the previous one we placed the alkyl ring. Lewis acid again is required as a catalyst, just like the previous Friedel-Crafts alkylation. Same Lewis acid is used, aluminium chloride, and the reactant donates the acyl group to the benzene molecule, which we can see is attached here. So the C double bonded with O and a CH2 CH3 molecule. This is the acyl group, and its ionic form, or the cation, is known as the electrophile. So the one with the positive charge again in this reaction as well is the electrophile. When this molecule attaches with the benzene, it loses the positive charge. Other product is the same hydrochloric acid. Next up is the oxidation of the alkyl benzenes, and there are a few different types of this oxidation reactions in which mainly the loss of electrons happens. And for all of these reactions, we need a few molecules as catalyst, like this top one, or sodium dichromate is required. Sulfuric acid is also required. Water and heat or high temperatures is also necessary. So whether the benzene has an alkyl group or a simple alkyl group like this one, which is the methyl group, or it has a bigger alkyl group, all will result in benzene attached with the carboxylic acids. So the carboxylic acids will be the product. As we can see here, COOH is the carboxylic group. And a very important thing to remember, which can be important from exam point of view, is that if the benzene is attached to a alkyl group which has a tertiary carbon, as mentioned here. So 3 degrees is what we call the tertiary carbon. It was there before in one of the previous lectures as well. Simply, this tertiary carbon means that this carbon is attached with no hydrogens. So there is no CH bond in it, no hydrogen is attached with it. Such a carbon is called a tertiary carbon. So if the group has the tertiary carbon in it, then no oxidation can take place. So no reaction will occur if the benzene has got a tertiary carbon in it. That is the important thing to remember, even if we provide with all of the factors that we usually provide for the oxidation. So we have a couple of examples of this oxidation of the alkyl benzenes. To remember again something from the previous slides, that this molecule, which has a benzene attached with a methyl group, has a common name known as toluene, and plus this one also has a nitro group. So this one is called p-nitrotoluene, and P represents the attachment of the groups on carbon number 1 and carbon number 4. So we don't have to write the full 1-methyl 4-nitrobenzene. Instead, we have used the common name or the historical name, you can say, which will be p-nitrotoluene. So all the previous factors of oxidation has to be there: sodium dichromate, sulfuric acid, water, and heat, and we get a carboxylic acid, which is p-nitrobenzoic acid this time, which has got a carboxylic group attached in place of the methyl group that was there in the reactant. Similarly, another example of oxidation of the alkyl benzene is there. Different groups are attached this time. One is the same methyl group, so the molecule is toluene basically, and we have a propyl group at the other end. So this whole molecule will be p propyl toluene, and the same factors of oxidation again there, that will result in a dibenzoic acid this time, which has got a carboxylic group at carbon number 1 and also at carbon number 4.